Okay, so let's begin. So first of all, what is an assembly language? Assembly language is basically, you can see in this picture, just first of all, there is hardware. Above the hardware, there is machine language. And then comes the assembly language. Assembly language is, you can say, one level lower than some high-level languages like C and C++. And every C++ code or C code, we can see in the logs that it uses basically assembly language. Yeah, we can use assembly language to reverse engineer, and it's very useful. And this is how it looks like, assembly language. This is just the beginning, and these are the imports like in Python, and this is the data. I will explain everything in detail later. And this is the code. This is not important. Yeah, okay. So first of all, how is data stored? So as you know, the data is stored in zeros and ones in computers. In every computer, the data is stored in the form of zeros and ones, and that too because of in hardware it's possible because of gates and electronics and stuff. That's why we are able to represent basically Boolean value of true and false. Either a circuit works or it doesn't work. Either a circuit is open or the circuit is closed. That's how we are able to uh, differentiate between 0 and a 1. And this 0 and a 1 is called a bit. So one bit has two possible values, 0 or a 1. But we cannot do much with just one bit. We can just represent a true or a false or a 0 or a 1. So if we make two bits, then there are four possible values. For example, this is a 0. Four possible values means there can be a 0, 0, 0, 1, 1, 0, 1, 1. So these are four possible values, and we usually um, represent them with the number 0, 1, 2, and 3, four possible values. But still, this is two bits are still not enough. Now we move on to four bits. So now 16 possible values, and 0, 0, 0 here means 0. And how will 1 be represented? We can represent 1 by first of all trying to add 1, and when we add 1, becomes 0, 0, 1. And when we try to add another one to make it 2, we get 0, 0, 2. But no, that is not possible because we can only represent zeros and ones. In any computer, it's always zeros and ones. So that's why it's not possible to represent 2. So what we do is basically, so when we try to add 0, 0, 0, 1 plus 1, what happens here is that 1 plus 1 becomes 0, and 1 gets carried on to the next higher order. This becomes 0, 0, 0. 0, 0, 1, 0 has 2. And when we try to add another one, you can see we can just directly add here because 0 plus 1 is 1. It becomes 0, 0, 1, 1, which is 3. And again, when we try to add one more one, here is a example. So 1 plus 1 is 0. 1 gets carried on. 1 plus 1 is again 0. Come on, let's carry on. And this is how we get 0100, which is 4. And yeah, this is how we can represent like almost exactly 16 values. And the final value is when all are ones, that is 15. But again, 15, 16 possible values is still not enough. We perform so much complex calculations in this age. So that's why we move on to a bit more like 8 bits. Instead of 4, now we have 8 bits, and now you can see there are 8 bits and there are 256 possible values. Now we can use this somewhere at least. And when we try to represent something, we represent it like this. So, for example, this. But what does this mean? We can't, on top of our heads, know what this binary value mean. So what we do is we do this. So if it is a binary, ones and zeros are possible, two possible values, we give it power from left to right. 0 power, 1 power, 2 power, 3, 4, 5, 6, 7. And we use these numbers as coefficients. So 0 times 2 power 0, 1 times 2 power 1, 0 times 2 power 2, 1 times 2 cube, so on. So here you can see this will be 0, this will be 0, 0, 0. So and the first value is 1 times 2 cube. That's why we wrote 8 here. And the second value is 1 times 2 power 1. So we wrote here. This binary value can be uh, changed into what we know, which is 10. And now, what are computer data types? First of all, computer data types. So we learned about 8 bits. 8-bit can be, we call 8-bit in computers as, so 8 bits can be named as a byte. Similarly, 16 bits can be named as a word, and 32 bits are known as double word. See it here, word, double word. You can see in a byte there are 8 bits and 256 possible values. In a word, this many possible values, and in a double word, these many possible values. Okay, so a simple question: if we want to write 2 in a in byte, which has 8 bits, we can write it like this. So 8 bits, or we can write it 0, 0, 0, 0, 4, 0, 0, and 0. This is number 2 in byte format, and we will use this more later. So first of all, yeah, if we want to represent 2, we have to write these many numbers. If we want to write 2 in word, we would have to write 0 like 16 times. That's a lot. That's why we have different types of numeric representations. So binaries, first of all, that's what we learned here. And decimal is the one we know, the normal numbering. And the one that is most used in computer language is hexadecimal. In hexadecimal, there are 16 possible values, and we, instead of working with tens and 10 numbers, we work with 16 numbers. So how do we represent the extra numbers? So first of all, 0 to 9 is just a simple numbering, and after that it's alphabets. So 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, and lastly 15 is F. So hexadecimal works like this. And yeah, if we try to, um, yeah, we wrote 2 in binary in byte. So um, in hexadecimal, each 4 bits turn into 1. So because you can see here there are two possible values, two possible values times two possible, that is 16 possible values. And in hexadecimal, each digit here has 16 possible values. That's why 4 of the bits, you just write it as 1. And here as well, there are 16 possible values. 16. This is hexadecimal in 1 byte. As you know, byte has 8 bits. So one these 8 bits have 2 in binary format, and now these 8 bits or 1 byte has 2 in hexadecimal format. Similarly, if we want to write 10 in hexadecimal in a byte, so we make a byte like this and we write 0 and A is, as you know, 10. Similarly, if we want to write 10 in hexadecimal in a word, so we have 2 bytes, we just write it as 00 and 0A. So 2 bytes, 1 byte here, 1 byte here, and 1 byte is 16 bits. So 16 bits here and 16 bits here. Similarly, if we want to write double word, it is 4 bytes. So this is 8 plus 8 actually. 8, 8. And here 8, 8, 8, 8. Yeah, but how do we actually convert it? So to convert from decimal that we know to hexadecimal, we what we do is basically divide the decimal number with 16. For example, if we want to convert 29, which is in decimal, to hexadecimal, what we do is we divide this number with 16. When we divide it with 16, we can see that it becomes 29 divided by 16. It goes once. So when it goes once, the remainder is 13. So 16 plus 13. That's why, and what we do here is we pick up this 1 and then we pick up the remainder. And as you remember that uh, this is the same case as decimal, we wrote like 2 power 1, 0 times 2 power 1 plus 1 times 2 power 0, like this. Similarly, the hexadecimal we can also represent as 1 times 16 power 1 plus 13 times 16 power 0, or basically 16 plus 13. 1 times 16 plus 13. That's why we write 1 here, and 13, which in hexadecimal is D, we write it like this. So this is 29 in hexadecimal format. Similarly, if we want to represent 80 in hexadecimal format, we divide it by 16 and we see it goes 5 times with 16 plus remainder is 0. So that's why we put 5 here and then we write remainder is 0. Or basically 80 plus 0, and 80 is 5 times 16, so 5 here, and remainder is 0, so 0. But how do we differentiate? For example, if you are given two numbers 80 and 50, what do you mean by 80? Like it can be in hexadecimal as well, it can be in decimal as well. So that's why in computer language we represent these numbers with by writing the first letter of the format in front. So 80 in decimal is written as 80D, or 50 in hexadecimal is written as 50H. Now, this is a question. So, we want to write 129 decimal in word to hexadecimal. So, first of all, what is a word? A word is basically 2 bytes. So, first of all, this is the first byte, this is the second byte. And if we want to change this 129 into hexadecimal, we divide it by 16. So 129 divided by 16 should be 29 divided by 16. 16 times 1896, and then 612, 128. That is 8 times. 8 times. Yeah. And that is 1. So what we got here is 8. So 8 times 16 power 1 plus 1 times 16 power 0. So we pick this 8 and we pick this 1, and this remains 0, 0. So the answer is 0081H. That's how we represent 129 decimal. That's how we convert 129 decimal to hexadecimal in word. And if it was in just a byte, we will just write it as 81. Now next is, how do we convert negative decimal to hexadecimal? For example, we want to convert -11 in decimal format, which is in word, to hexadecimal. So what we do is, first of all, we write the positive value of this number. So 11 in hexadecimal is, in word format, is 0, 0 and 0B. And this is how we write 000BH, and it's in hexadecimal. What we do is we subtract it basically with uh, one extra digit. So for example, if we try to do with -8, let's do it with -8. So -8 in, let's do in byte first. We represent this in byte, the positive value of 8 is 8, -8 is 8, and in byte format is this. This is in hexadecimal, 08H. What we do is we basically subtract this value from one extra digit, so 00H, like this. We When we try to subtract, here is a difference that, like, we have to subtract in the form of hexadecimal. So for example, if we subtract form of decimal, 100 minus 8, what used to happen here was that we changed this into 10, this into 9, this into 0. So 10 minus 8 is 2, and 9. So 100 minus 8 is 92. So what we did here is took 1 from here, and then it had just 9 left, and then it also borrowed 1 from 0. Similarly, we will do the same thing here. 16 here, 15, and here is just 0. So 16 minus 8 is 8, and 15 minus 0 is 0, but 15 in hexadecimal is F. So the answer is F8H. So minus 8 in hexadecimal is F8. Similarly, minus 15 decimal to hexadecimal in double word. So first of all, we write the positive value of this in double word. The double word has 4 bytes. 1, 2, 3, 4. And in hexadecimal, we represent 15 with just F. F here, 0, 0, 0, 0, 0, 0, 0. So what we did last time too, we subtracted it with one extra digit. So 0, 0, 0, F. When we try to subtract, this is 16, this is 15, or just F, 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 15, 15, and this is 0. So 16 minus F, 16 minus 15 is 1, and everything else is F for the left. This is the minus 15 decimal to hexadecimal. So this is hexadecimal representation of minus 15, and the format is double word because there are 4 bits, 4 bytes. That's what it's done here too. So decimal, binary, hexadecimal, octal we won't need. Mainly we will need hexadecimal, and we have byte, we have a word, we have double word, and yeah, that's basically it. Yeah, and I will give some questions, example questions to solve. For example, convert minus 35 decimal to hexadecimal in word form. So word, as you remember, has 2 bytes, and minus 215 decimal to hex in double word plus 93 to hex in byte. Yep. Just solve these questions and send me, and I will verify them. Then you can also ask some doubts if you have. And in the next video, I will explain what are registers and how data is saved in memory. And this will be an important topic because it will have directly questions from um, So in the midterm test, so hexadecimal representation of integer numeric values of signed and unsigned. Signed is minus, unsigned is without minus. So that's what we practiced a bit, hexadecimal representation, what is hexadecimal and how we convert from decimal to hexadecimal. And now in the next video, I will explain registers in memory. So how these hexadecimals are saved in registers in memory, and that's where we will get questions from. Like here you can see FFC hexadecimal is very important to know, and you can see 0A, 01, and here as well A7FB, and here yeah, in the next video I will represent memory in hexadecimal, and you will be able to solve task 1, 2, 3, and 4th. Yep. Okay.